As the final lecture for Rust concurrency libraries, we're going to study Crossbeam, which is concurrency libraries in Rust that is widely used in many programs written in Rust. For example, it is deployed to Firefox. I am one of the maintainer of this Crossbeam, and so I contributed to the implementation of many of those libraries. And so that's part of the reason why we study the Crossbeam here. I know internal details to the Crossbeam. So first API we want to use is what is called Sculpt Threat. Recall that in Rust standard library, the thread spawn function requires that the function f here and the return type should be statically scoped. That means that you should be able to move the data to the end of the program. But it is sometimes very much too much constraint. So we want to, for example, declare a stack variable and share it with multiple threads. The standard library scope thread, library thread doesn't allow that because the function type and the return type should be statically scoped. On the other end, this Crossbeam Sculpt Threat relaxes the constraint and allows principled sharing of scoped variables. So, example is easier to learn the thing. So, in this example, that is copy and pasted from the Crossbeam documentation, it is creating a string that is written hello world. This is called a greeting, and greeting is shared with two threads. Two threads are spawned here, and each thread is immutably borrowing the greeting variable, and it is just writing it to the screen. So let's execute it, and the two threads are writing or printing the greetings here. So far so good, but it was impossible using the standard library's thread spawn function. The reason is that the function here and here should be statically scoped in standard library thread spawn function, and as a result, you cannot pass the reference to the stack variable. So in order to pass the stack variable's reference, which is not statically scoped but scoped within the main function, then the scope thread should be used. Why is it safe? The reason is that the scope is first defined before spawning threads, and the scope S is defined here, and then the threads are spawned. It is guaranteed that by implementation of this scope thread, at the end of this scope thread here, then all the threads that has been spawned inside this scope thread should be joined. And as a result, at this point of time, there is no longer a reference to the greetings variable. So that's the reason why this greeting can be shared among multiple threads, because it is guaranteed that all the threads are guaranteed to be exited before greeting is can be dropped. That's precisely the reason why the standard library thread spawn required the static scope. Greeting can be dropped before the thread has used it. But it is not the case in scope thread because the threads must exit before greetings are dropped here. So that's the one of the motivation of the scope thread, and it can be very much useful when you want to just spawn threads and wait for them and share some data across multiple threads. That sharing is usually very much difficult to do so in C and C++ because the sharing, when you have a tiny misconception of the lifetime and scope, then your program will become buggy, and you will have a very difficult to find bugs in your program. However, in Rust, the Sculpt Threat API has a safe API only, and that's precisely the reason why we can do this. We can share data across multiple threads in a principled way without worrying about the possible unsafe behaviors. So far, so good. And the next API we want to discuss is what is called cache padded. In concurrent library, it is very much common to do file sharing. File sharing is that suppose that there are 3 agents, P1, P2, P3. Here P should probably mean processor, but let's say they are threads. There are thread 1, thread 2, thread 3. And they are accessing their own data. So it is the same thing, but it is cached into each CPU. And the P1 is accessing the first data, P2 accessing the second data, P3 accessing the third data. They are accessing the same cache line, but with different index. So they are accessing different locations, but with the same cache line. The problem is that if the P2 writes some value to here, then what is happening here is that it should invalidate the other thread's cache lines because they all share the same cache line. So if P2 is writing a value to this cache line, then the other's cache line should be invalidated. That's the reason why the cache traffic is happening here. But it can be detrimental to the performance because even though multiple threads are accessing their own data without any sharing, we hope that the threads doesn't interfere with each other and get the full performance. But because the data is put in a single cache line, the write to the one cache line is affecting the others. They should invalidate the others' cache lines. It will be very much detrimental to the performance. Even though I am not reading from and writing to the others' data, my cache line is evicted. So this is basically what is called false sharing. They are not true sharing because they are accessing different data. But they are still false sharing because they are sharing the same cache line. So the moral of the story is that when you are doing concurrent programming, then you should guarantee that multiple threads are accessing different cache lines. So that is the moral of the story. And this cache padding allows you to do so very easily. So this is basically padding data, the underlying data T, with cache line boundaries. If the underlying data T is 8 bytes, then cache padded will be 64 bytes or 128 bytes, depending on the architecture. So it is basically padding zeros around this type T to make it multiple of the size of the cache line. So as a result, this can be used to represent data for concurrent data structures, and it is guaranteed that multiple locations are not falsely shared. So for example, we are going to learn Q at the later stage of this course, and Q has 2 pointers basically. 2 pointers. One pointer is to head of the queue, and the other pointer is the tail of the queue. And they should be concurrently accessed. It is the motivation of the concurrency of the queue. Push and pop side are concurrent, and they should be somehow concurrently accessed. But if they are put in a single cache line, then it will be detrimental to performance because all the operations on the head and all the operations on the tail should be interfering with each other. We want to avoid that. That's the reason why we cache padded the head pointer and tail pointer on their own, and now the cache lines are different and the operations are not interfered with each other. So that's basically the motivation of cache padded, and it is very easy to use. And please memorize this picture. What is the meaning of fault sharing? And when fault sharing is suspected, then please use cache padded. It's very much easy to use. And the final API we want to study is what is called channel. We already saw a little bit about channel. So channel is already in standard library. It is MPSC channel. That means it has multiple producer and single consumer. MP means that multiple threads can push the data to the channel at the same time. That's the reason why it is multiple producer of the data. On the other end, it has a single consumer, which means that only one thread can pop the data from the channel at one time. Only one single consumer. That's the reason why it is called MPSC. Now you can imagine that there are SPSC, SPMC, and PMC. It is multiple or single producer or consumer. And this Crossbeam channel is MPMC, which means that it is multi-producer, multi-consumer. So it is the most general form of channel. Multiple consumers and multiple producers are at play at the same time. So you can create it by calling what is called unbounded, which will create an unbounded channel with unbounded capacity. You can put as many as possible data into the channel as far as your DRAM has a capacity. There are also bounded channel, which has a bounded number of messages, and when you want to put data into this bounded channel and it is full, then it is going to return error. So there are the API usage, but it is very much simple. Just multiple threads can have producer or consumer. I mean, they can have a sender or receiver or transmitter or receiver, and they can have multiple senders as well, and they can just send data. And it is just acting like a channel, like in Go or Python. So it is very much easy to use, but the internal implementation will be a little bit difficult. So I will explain the internal implementations at the later stage of this course. At this point of time, just look at the code and see, oh, it is not very much difficult to understand. Okay, so far so good. And there are basically the API is very much easy to use, so please read the documentation. And what is quite interesting about channel is that it provides a macro that is named select that is trying to receive or send from multiple channels basically. So if it wants to receive from multiple channels, then you are going to use this select. When you are receiving a data from this R1, which is this unbounded channel, then you are going to do this. And when you are receiving a message from R2, then you are going to execute this. It is doing this at the. It is trying to receive a message from multiple channels basically at the same time. It is much more efficient than looping over all the channels at the same time. So it is basically an optimization for working with multiple channels. So for example, in the implementation of actors or other kinds of libraries, then this feature, the select feature of the channel, will be very much useful. So we will discuss this aspect at the later stage of this course. So This concludes our discussion on the log-based APIs, log-based concurrencies APIs. So please look at all the definitions of the structure that we have learned so far, and please read the documentation. So usually the Rust concurrency libraries are well documented, and they explains the things very clearly a lot. So please read the documentation and try to learn something from these documentations. If you have any questions, please read the documentation and then ask the questions in the issue tracker so that we can answer your questions.